the last talk of the session by Daniel Neal on phased LSTM, accelerating recurrent network training for long or event-based sequences.
Hi, everybody. Thanks for staying around. So I am talking about phased LSTM here. That's going to be a neural network model that we came up with that we hope offers some interesting advantages for particularly long sequences or sequences that are sampled from data that is asynchronous in nature. So first, let's start off by kind of motivating what I'm talking about here. So I want to think about what the frontier of RNNs and data is right now. So what are the problems that are very difficult for RNNs to solve? So I'm going to highlight 3 of them. Here's the first one. So extremely long sequences. If you think about your average movie, about 2 hours long, somewhere between 30 and 60 frames per second, it comes out to about 234,000 frames for a single movie. Similarly, for a book, you have 100,000 words. Financial data is quite voluminous, so you get 20,000 transactions per second. In general, empirically, I find that under standard conditions, training RNNs that are greater than 10,000 time steps in length have serious difficulties. So we hope that this particular model can help address some of that. Another common problem for recurrent neural networks is integrating evidence from multiple sensory systems. So if you take this kind of adorable self-driving car, and you can imagine that it has sensors on it that are vision sensors running between 25 and 60 or 100 frames per second. You have gyroscopes or accelerometers running at 1 kilohertz. You might have a LiDAR system that's as slow as 5 hertz. And you somehow need to integrate all that information together. And it's not an easy thing to do in a recurrent neural network. You either have to skip some of that data, or you have to run it at the fastest possible time step and repeat input information. Finally, there's a form of data that's starting to emerge from these event bio-inspired sensors. So here I've highlighted data from the dynamic vision sensor. It produces output events when pixels change in contrast. And one challenge of dealing with this data is it just produces an extremely long event sequence, and this event sequence is essentially asynchronous in nature, resolution of about a microsecond. Now, if we think about all these things put together, the one problem that they seem to all share is that we want to be able to process all the time, many time points, but practically we can't do something like that. So I wanted to think about this question: how do you process all the time points without actually processing all the time points? And it turns out that there is possibly an answer for that. So we looked at out-of-synchronous sleep-wake rhythms. So with sort of inspiration from biology and some previous work in recurrent neural networks, think about this situation. If you have an input stream at the top, where input events are denoted by vertical lines across a time axis, you can imagine that that first event that you see at the far left of the input stream occurs during the sort of on or awake state of neuron 1. But unfortunately, that corresponds to the off state of neuron 2 and 3. And it's reversed for the second half of that cycle. The later spikes come in during the off part of neuron 1. Now, the advantage of doing it this way is that you're always paying attention to the input. At some point in time, if you have a sufficient diversity of frequencies of sleep-wake rhythms, there's somebody paying attention to the input. But you never have to incur the full cost of a computation. You only have part of your network ever doing its actual work. So how would we implement that? A good place to start is a state-of-the-art neural network model like long short-term memory. So we begin there, and we can add a new gate, which we'll call the Chronos gate for time, KT, and I've drawn it here as a mux. And it's a mux because it looks at the actual time signal coming in from the outside. This is kind of an external signal, not necessarily part of your input, that keeps track of real time, a number between 0 and positive infinity. And it takes this time and allows the cell of the long short-term memory to only be updated when that gate is opened. So more formally, we have these parameters here, the phase shift S, the period tau, and the on-off ratio of open to closed. So on the left, we represent phi, which is its position in phase space. So we take the timestamp, we pass it through a mod function, and that gives us a position in phase space, whether or not that neuron should be open or closed. Importantly, every one of these neurons has its own parameters for this cyclic oscillation. And on top of it, these parameters are learnable, the way they're defined here. It's piecewise differentiable, and because we have a small leak during the off state with analogy to leaky ReLUs, we can effectively train all three of these parameters. And it actually does make a difference. Some previous work by Schmidt-Huber on clockwork RNNs, or previous work from Bengio has also kind of looked at these different timing strategies of RNNs. But one unusual thing about this particular paper is that we are using ones that can be trained. All right, so let me give you some intuition of how this works. So on the previous slide, I mentioned that we only allow the cell state to be updated when the KT gate is open. What you're seeing is a video of a very simplified schematic of how this thing works. We have two plots. On the left, we have a view over time of this network. So it's across all time on the x-axis. On the right, we have an instantaneous view from the network's perspective. The input is a single scalar, and we have many cell states CT. Now, the only real thing I want you to pull away from this is that the neurons update their cell state CT only when these gates are open, and that corresponds to when the black-white gate status turns white. During that period, the cell state updates with the new scalar value and stores it. The current time axis is marked by that red line that's slowly moving across on the left-hand side. All right. So even just with that view, it might start hinting that there are some interesting advantages to this model, and I'm pointing out two of them right here. So the first is that these different phases delay the history in unique ways. So every neuron has trapped a segment of the past at the current time point. So if you look at a sort of vertical line through this left diagram, what you see is that some of the neurons will be paying attention to the time far ago in the past, the blue areas. Some will be paying attention to more green areas. Some are almost yellow. And if you think about that, this could really help learning to incorporate arbitrary alignments between your data with different lags. Additionally, we can offer large savings in compute. So here, what I typically used during training these networks was a ratio of on to off of about 5%. So 95% of the time, this network isn't doing anything. Now, during training, you have this leak so that you can actually properly train it. But at test time, it really is off. Those things do not compute at all. Unfortunately, sparse libraries for matrix separations aren't quite there yet with giving us significant advantages. So these are more still theoretical advantages. But as of CUDA 7.5, the GemVI instructions add this like dense matrix times sparse vector multiplication, which is what we need to make this thing really effective. And it's only going to get better over time. All right, so what I'd like to show now is a very simplified diagram of this phased LSTM in practice on a real task. I'm specifically designing this task so that it stresses certain aspects of the model, and it's particularly favorable for phased LSTM, so, caveat there. Basically, we have two classes. We have input sequences, which are just sine waves, and we sample them at points here represented by circles. And we have one class, which corresponds to a period of 6 to 7 milliseconds, and then we have another class, which is everything else, either faster or slower. So we want to find these green check kind of sine waves in our input and mark those with a 1. Now, what we do is we expose it to 3 different sampling conditions. So under the standard sampling condition, which corresponds to how most people use RNNs right now, we have a discrete time step that's fixed in length. Here it's 1 millisecond. And we have a reasonable number of input points. Here about 100 input points. So the network receives 100 input points of a y position and a time, and using that information, it has to decide the frequency of the underlying sine wave. We can see that phased LSTM solves this well on the far right plot, but also batch normalized LSTM and regular LSTM also succeed at this task. Now, if you sample that same input 10 times faster, which has 2 effects. 1, you change your input sampling rate, but 2, you actually lengthen the training data that you give it. Now your input sequences are 10 times longer, which decays the gradient substantially when you're trying to train. We see that for the same number of epochs, LSTM and batch normalized LSTM have a much harder time of learning this particular task. Now, presumably, if you let it run out for longer, it would actually solve this successfully. But interestingly, as intuition might inform, phased LSTM actually does better. So the accuracy increases almost up to perfect accuracy. And finally, we want to test how well it understands time. Instead of sampling regularly, we sample at asynchronous times, just arbitrary times, pull out a time point and a y coordinates, and we feed this information into the network. And again, for the same number of epochs, phased LSTM does substantially better. Now, that's a little bit of an artificial task, so we try and make it a little bit harder. One thing we can do, because most time series are composed of multiple frequency data, we can start adding more frequencies to the input sequence, and again, do the same task. So what we can do is we stack the input frequencies together. We try and discriminate them so that we find the particular frequencies we care about. When we test that, we find out that phased LSTM does substantially better. And what I hope you see here is something that we'll see in a lot of the examples. Phased LSTM tends to learn very quickly and very robustly compared to alternative models. Now, even for more standard tasks, such as the adding task, where you present this input string of numbers and you mark certain of those numbers with ones, the job of the network is to produce the sum of those numbers. We can show that we converge very quickly with that. And interestingly, we can converge with a speed related to the period parameter that we choose. If we choose a longer period, the network trains faster. And this is because this on-off cycle acts kind of like a wormhole for the gradient. You have the strong gradient coming in one end, it falls asleep for many hundreds or thousands of time steps. When it finally reopens, it still has that potent gradient to train with. All right, now, so the last example I'd like to show is sensor fusion. So we need a data set that has two different types of input. In this particular case, we take the grid corpus, which is video and audio of spoken sentences, which are relatively simple, like set white with P2 soon.
Set white with P2 soon.
And we train a neural network to try and solve that task. So here's the architecture. We choose the audio MFCCs to come in at either 25 hertz or 100 hertz, and then go into a phased LSTM layer, followed by two merge layers. On the video side, we have a CNN to pre-process the image, feed into a video phased LSTM, and then the upper layers are basically tasked with learning integration of evidence across the two data sets. So here's the way that we set up the open gates. So the audio phased LSTM, we know the sampling rate a priori, so we can set those opening phases to directly coincide with the MFCs that we receive. Similar with the video phased LSTM, since we know the sampling rate a priori, we set the rhythmic parameters to coincide with that. The upper layers, we don't know what kind of timing they would prefer, so we initialize them with a rich set of dynamics and let gradient descent to take care of the problem for us. When we finally test this system, what we can see is that for kind of a standard situation where you have your video and your audio and they're the same length, the same sampling rate, batch normalized LSTM does very well. Phased LSTM, however, it still does a little bit better. Once you increase your audio input stream to 4 times longer, where you're sampling at 100 hertz, in this case, only phased LSTM was able to learn in this amount of time epochs. So that brings me to my conclusion. I hope I've convinced you that phased LSTM can offer many advantages. So we seem to be able to demonstrate that it has this very fast convergence to long inputs. And this is to bring us back to that first slide. What are the problems in the frontier of data and RNNs? So now we can solve maybe longer input problems with this human tunable tau period parameter. We can naturally integrate evidence from multiple sensors, depending on whatever their timing rate is. Importantly, we can also use asynchronous sensors or real-time data streams as well, because it synchronizes based on the true time that underlies those sensors. As a kind of an added bonus, it has very sparse computation, right now theoretical, but hopefully soon practically as well. And amazingly, it's easy to implement. So you basically just hijack your mask function, you add an upslope and a downslope and a leak when you're off, and you're good to go, you're golden. For me personally, I think one thing that I like so much about this model is that it has many intriguing properties. These sleep periods act like dropout and regularize the network for robustness, it seems. And these are all kind of ideas of ongoing work. The long sleep periods can preserve this back-propagated gradient. This is what I was referring to earlier. So during the time that it's asleep, that gradient is not being perturbed by all the other input data. Finally, and interestingly, these neurons act like a set of basis functions that do a learnable gated frequency transform of your data. And that's probably a good thing for time series data, so it's an advantageous thing. At this point, I'd like to say that this QR code goes to the paper if you're curious to read more. I will be at the poster session today from 6 to 9:30, poster number 189. Happy to talk to anyone about it. I think it's a really interesting model. Send me an email if you like. I'd like to thank the Sensors Group, of which I'm a part, University of Zurich and ETH Zurich, the kind people for funding me, and my amazing two advisors, Chi and Michael Pfeiffer.
Time for questions. In the back, yes.
Thank you so much. This was a great talk. I wondered, you talked about how when there are different phases, they sync up at different time points. Have you tried to optimize for that? Because you can choose phases that will sync up with minimal frequency.
Yeah, it's a great question. So one challenge that phased LSTM is that you need some amount of diversity of responses in order to share information between neurons. And it's sort of like most degenerate form where it's entirely open, they're entirely synchronized, but then it's just regular LSTM. But I think you're hitting on something really great, which is this idea of maybe synchronizing somehow to your input. Somehow, you could imagine it latching on to the start of a word or a phrase in speech processing and sort of synchronizing to the rhythmic nature of lots of different time inputs. It's an area of ongoing exploration. I'd love to talk to you some more at the poster session about it if you're curious.
Cool, thanks.
Another one in the back, in the center.
Actually, it was a very similar question, but I was wondering what was the distribution of frequencies with human speech, the test you were doing, and if it matched human speech, and if you'd compared it to noises and noisy speech or other sorts of sounds.
Yeah, so it's a great question. So basically what we do is we just start by initializing these neurons with a very rich set of dynamics. In this particular case, we didn't actually see the effect that we expected to see. We expected, as you might imagine, to pull out rhythms that correspond to the various frequencies of, phonemes, words, sentences, conversations. We didn't get that richness out of it. It's something very interesting. It seems to somehow use the beat frequencies between the neurons. But I think it would be a great extension to the model, for example, to work on like having it latch onto particular input frequencies.
In the front, yes?
Yeah, I was going to ask, do you think there are some disadvantages of this model compared with a normal LSTM? And then I just also, for clarification, when you're comparing asynchronously, do you also give like some time step information to the RNNs?
Yeah. So, okay, second question first. When we compare asynchronously, we basically just feed the time, the time value that the time gate would receive in phase LSTM as an input to the other networks.
Yep, okay.
Sorry, what was the first question?
First question was, do you think there are some disadvantages of this model versus a standard LSTM?
Yeah, so unfortunately, although it's far sparser, it takes longer to train right now. So I just did a benchmark over the weekend, actually, and it's still faster per input sample in terms of convergence. You will, at least on some tasks, train more quickly using this more complicated model. But compared to other simpler models, the extra parameters you have to backprop through can double the training time.
Okay, thanks.
Okay, I'm going to go on the left here.
It was indeed very interesting talk. Thank you very much. So my question is about the scaling of your phased LSTM. So in one of the examples, you essentially were distinguishing frequencies. So essentially, phased LSTM was doing some sort of a Fourier transform inside. So if one starts increasing the frequency resolution, so if you can discriminate between more and more frequencies, would be the scaling behavior of how many neurons you need per kind of resolved frequency in frequency domain?
Yeah, it's a good question. So I think I would use this particular task more as a way to stress certain aspects of the model rather than use it as a task to solve explicitly. I mean, I think if you took like a Fourier transform of this input sequence, it would be perfectly separable. It would be super easy. So maybe it's not the correct way to solve it in general, other than to test certain aspects of this model. Now, as to how it would scale with increasing resolution, I mean, ultimately, it is a discrete model. So it's a data-driven model. You sample the phased LSTM when you receive data. If you go down arbitrarily small, it becomes something more like a continuous model, which would be substantially harder to both train and predict, I guess. So I think the short answer is I don't know, but it's very interesting.
Okay, thank you.
Okay, and one last question right in front here.
Hello, I wanted to ask, have you performed any tests to see how complete is coverage of like past, if you say vaguely, like the past signals? Like how, is there a way to compute, like some way to measure that?
Yeah, so yeah, for sure you want to ensure that someone in general is awake and paying attention to your input. So what you can honestly do is you just run it out for a fixed amount of time at some resolution that you care about, and then just sum up the columns of who's awake. And it turns out that generally if you initialize it with rich enough dynamics, and you have a reasonable number of neurons, like 100 to 500, then you're pretty much guaranteed that someone is on and paying attention. Yeah, if it's important for real-time sparseness, you can increase that the sparse, you can basically go down in resolution, or you can go down to like 1 or 2, but in general, normal conditions are sufficient.
Thank you.
All right, so we'll end here. Let's thank our speaker again.